For decades, online education has relied on a deeply flawed metric to measure success: the end-of-semester student survey. By the time an instructor reads the feedback, the course is over, and the opportunity to help struggling students is already gone. Current evaluation models look almost exclusively at static infrastructure. They measure video resolution, support system availability, and syllabus layout, ignoring how students actually interact with the material. Meanwhile, the learning management system is quietly generating thousands of data points every second. Every click, pause, and keystroke is a piece of raw behavioral telemetry that usually sits completely unused. A 2023 paper by Yusuf Apta and researchers at the University of Guelma proposes a strict inversion of this model. They argue that accurate evaluation requires abandoning subjective surveys and instead using raw behavioral telemetry to measure real-time learning outcomes. To understand how this works, we need to reverse engineer their proposed architecture, the Quality Assessment System for Online Courses, or QASOC. QASOC is designed to take unstructured server logs and mathematically transform them into a single Euclidean vector. This outputs an objective numerical score for course quality. By shifting from subjective human feedback to algorithmic data processing, institutions gain the ability to trigger automated pedagogical interventions weeks before a student actually fails a test. The foundation of this system requires structuring a course into discrete blocks. Instead of evaluating a whole semester at once, the material is divided into specific learning objects. This tripartite engagement model sorts interaction logs into three distinct pillars. Cognitive engagement tracks physical effort, measuring time spent and interaction frequency. Affective engagement quantifies emotional investment through return visits and rating scores. Finally, academic engagement anchors behavioral data to test performance. Without this strict categorization, a server log containing 3 million clicks is useless noise. Separating the data into cognitive, affective, and academic streams provides the precise inputs required for the algorithmic processing that follows. There is an immediate mathematical problem with this tripartite data: scalar mismatch. You cannot run a direct mathematical average on variables that exist in completely different units. A student might generate 500 seconds of reading time, a Boolean true-false like status, and an 85% test score. To solve this, the QASOC system routes all raw inputs through a min-max normalization protocol. This equation takes the maximum and minimum values of any specific indicator and mathematically compresses every student's raw data into a uniform decimal falling precisely between 0 and 1. Once standard scaling is achieved, the algorithm calculates an average engagement score for each individual learner. Those individual averages are then compiled into 3 single, unified metrics representing the total cognitive, affective, and academic engagement for that specific learning object. Normalization acts as a mathematical bridge. It takes the erratic, highly variable nature of human web browsing and forces it into universally comparable data points. With the data cleanly normalized, the system moves the calculations out of a flat spreadsheet and into 3-dimensional space. This 3D grid maps the 3 pillars of engagement as X, Y, and Z coordinates. The origin represents total pedagogical failure, while the opposite point at 1 represents theoretical perfection. QASOC plots the class's actual data coordinate, then calculates its Euclidean distance from perfection. The math is finalized by taking the actual distance and dividing it by the maximum possible distance. This specific ratio generates the learning object quality value, giving the instructor a definitive, objective metric of exactly how well the material is performing. Pedagogical quality is no longer an abstract feeling or a delayed survey result. It is a literal, mathematically derived physical distance inside a vector space. Calculating Euclidean distances manually for every quiz and reading assignment would be impossible for an instructor. This diagram outlines the full QASOC architecture, processing calculations automatically. Raw telemetry flows into the pre-processing manager for cleaning, then feeds into the assessment manager to run Euclidean algorithms. Finally, if a module's quality drops below threshold, the system alerts the course creator. This architecture completely removes the burden of manual quality control. slow end-of-year instructor audits are replaced by continuous automated system diagnostics. To verify that this mathematical model actually translates into higher student performance, researchers deployed the system on a live cohort of 33 economics students at the University of Guelma. The experimental design established a pre-test baseline using standard course delivery, followed by a second phase where the instructor actively utilized QASOC's algorithmic interventions. This histogram tracks the results of a Welch t-test comparing the two phases. Following the data-driven interventions, the students showed a statistically significant improvement in their cognitive profiles. The researchers ensured statistical validity by running Kolmogorov-Smirnov and Shapiro-Wilk tests, confirming the data followed a normal distribution before calculating the final t-scores. Relying on subjective end-of-course surveys to evaluate educational materials is an obsolete practice left over from the earliest days of online learning. By engineering raw server logs into precise vector distances, institutions now have the capability to objectively quantify the quality of a course and automatically correct its failures long before the final exam is written.